Hey young innovators to watch, my name is Seon, and this is a demo of my phase 1 transcription factor binding model and how it works. So on a high level, it's basically a convolutional neural network, which is a deep learning approach that's traditionally used for image classification. And the way we translate it towards genomics research is we basically take genomics data, so A's, C's, G's, and T's, the four nucleotides that code for human life in DNA, and we basically convert it to four different channels using a process called one-hot encoding. So after we want to encode them into four different channels, it forms a 4 by M matrix, where M is the number of nucleotides. And this is basically the input into our deep learning model. So we pass it through a set of three different convolutional layers, max pooling, as well as fully connected neural network. And the output is basically 1 or 0, where 1 is bind and 0 is no bind. So the output would basically a probability of binding affinity, or how likely it is that a given CTCF protein will bind to a DNA. So it's usually a decimal between 0 and 1. And what makes the approach really interesting is what I did is I basically have an automatic training pipeline that allows me to basically at first it has a random weight initialization. And after training on a sample set of data, it picks the top five models, basically the models that perform the best five random weight initializations, and it tests that on the validation set. So basically, the goal of this is we have five models at the end, which are fine tuned on thousands of base pairs, so thousands of A, C's, G's, and T's, and have a really good understanding of how the CTCF transcription factor protein binds to DNA. And using this model, we can basically score an entire gene and create sequence maps. So what sequence maps allow us to do is basically uncover which base pairs are have a high likelihood of DNA protein binding. And from here, we can basically detect different mutations, potentially pathogenic or disease causing mutations. So basically, if we were to demo this, we would basically, I've already prepared basically the entire environment, including the pre-trained model, loading everything using a tool called Deploy. And now we just have to run the predictions. So basically, we'll take the final three commands and try to visualize the different scores that we get. So right now, what it's doing is it starts off by basically trying to get an example, and then it's basically trained to predict on an entire data set. So the model is already trained on the A549 chip-seq data set, but what we're doing here is we're taking basically a data loader from Kupoy and training it on a specific CTCF data set from Kupoy that's basically trained on that is basically data from the Human Genome Project. And from here, we can visualize how the model scores. So as you can see here, we output a model score. So it includes things like the chromosome, where the specific nucleotide sequences are, which specific base pairs have a high probability of binding. So if you look here, it basically identifies certain base pairs such as the 135,993rd base pair, and we can basically visualize these scores using sequence maps. So how sequence maps work on a high level is they basically allow us to visualize what are the strongest DNA protein binding interactions and which nucleotides cause the strongest protein binding interactions. So this is kind of a visualization from matplotlib that I made. So as you can see here, if you look at this specific base pair in the motif map, a C would indicate a really strong DNA protein binding interaction. So across this entire genomic region, what are the certain nucleotides that have the strongest likelihood of creating a positive DNA protein binding affinity, or increasing the probability that the CTCF protein will bind to a DNA sequence. So what's really cool about this project is we can basically do something called in silico mutagenesis. And what this means is we take every single potential mutation that can occur in a gene. In this case, we visualize the LDR1 gene. And in this visualization from Deep Genomics, they show that basically for any single point mutation, whether it's positive or negative, as well as how strong the interaction is. So similarly to how we map how strong the interaction is by the height of the letter, where a taller letter would indicate a stronger interaction, the same principle is applied here, but we also uncover negative mutations. So a common pattern here is that across the LDR1 gene or cholesterol gene, we see that Ts have a positive impact on DNA protein binding, meaning that T mutations increase the chance of a DNA protein binding interaction from happening. So that's phase one of my project, and phase two deals with using basically language models, some long models like LSTMs for molecular de novo design. So using SMILE strings, which are these computational representations of molecular structures. So basically, they're these large text files that have large-scale molecular molecular structures or chemical structures encoded in a text file. We basically train a language model on this to basically generate new molecular structures, and my approach generates valid molecular structures 84% of the time. And I trained it on over 100,000 different molecular structures that I found from a open source data set. So right now what I'm trying to do with phase two is basically targeting a specific inhibitor, such as a trypsin inhibitor, and trying to generate, basically using fragment-based drug discovery, different drug candidates or different basically candidates that can bind or basically stick to these inhibitors. So that's my Project Novo, and it's an AI and drug discovery suite of different models, and the hope is to basically develop models that not only can function as genome tools or tools to basically understand transcription factor binding or DNA protein binding interactions, but also build models, generative language models that can also help us and aid us in molecular drug design. So right now, if you look at generating drug candidates right now, we start off with 10,000 different lead compounds, and we end up with only one compound that makes it past clinical trials. So the goal with this research is to really try to bring that down from maybe 10,000 to 1 to maybe 5,000 to 1. So basically allow us to create more efficiently and better designed drug compounds for then testing in the lab, allowing us to bring down the cost since we're testing less compounds in the lab, which allows us to create cheaper, better drugs and further our understanding of the human genome.